Hi everybody, Justin here from chemistrynotes.com, and we're starting a brand new section today. This section is section 15 and it's called Applications of Acid-Base Equilibria. Now the last section, section 14, was titled Acids and Bases, and we learned about strong acids, weak acids, strong bases, weak bases, and for weak acids and weak bases we learned how to do ice tables or equilibrium expressions, right? Using the ice method, we were able to solve for the H plus concentration. And from that, we could use pH equals minus the log of H plus to solve for the pH of the acid or base solution. Now, in this section, section 15, which is kind of like a chapter 15, we're going to talk about something called a common ion, which is actually it's the anion of a weak acid or the cation of a weak base, and there's two sources of a common ion, either the weak acid or weak base, and then it's salt. All right, so I'm going to get into that. I'm going to write it all down in our notes. If you didn't understand what I was talking about, that's quite all right. We're just getting started on section 15. So, section 15, video number 1. It says, in this section, we're going to build on section 14 and consider more applications of acid-base equilibria. We will also introduce an additional type of acid-base equilibria. Those will be equilibria involving the solubility of salts or buffers. So that is not a very good definition of buffers. We'll have a better one coming up later in this video, but essentially a buffer is a weak acid, and that weak acid has a common ion that is also present in the salt. Same thing with a weak base. A weak base is going to have a cation that's also present in a salt that's dissolved in the same equilibrium environment. So there's the star right there, and it says solutions of acids or bases containing a common ion. What is a common ion? It's a new term for us. It's an ion that is produced in common by both the acid or base and the salt from which it comes from. Okay, so for example, if I have a general weak acid HA, the common ion would be A minus. And then the A minus doesn't arrive by itself. It has to have a cation with it. So like NaA or Ka, for example. So, and that's what the arrow says there underneath solutions. It says solutions that, for example, contain not only the weak acid HA, but also its salt, such as NaA or Ka, etc. These are what constitute, or these are what make up a buffer solution. And we'll get into buffers later on in this video. I'm just building up to buffers right now. All right, so that's it for page 1. If you take a look at the top of page 2 here, there is a bullet point, and this bullet point says the following. It says the addition of a common ion, such as A minus, that's already a part of the acid's equilibrium expression, and that common acid I have is HA. So I just have a generic HA acid, weak acid, and the common ion A minus. So the addition of a common ion A minus that's already a part of the acid's equilibrium expression will cause a shift in equilibrium according to Le Chatelier's principle. Okay, that's why it's called a common ion. It's already a part of the dissociation of HA into H plus and A minus as products. All right, now that shift that has occurred by having an additional source of A minus, an additional source of the common ion, is called the common ion effect. Okay, and this shift is going to inevitably be a shift left because the common ion, the A minus, is found on the right-hand side or product side. All right, let's do an example to show how this works. In an experiment, it was found that the concentration of H plus at equilibrium, sometimes I drop off the EQ, right? In an experiment, it was found that the H plus concentration in a 1.0 molar HF solution was 2.7 times 10 to the minus second molar, and the percent dissociation was 2.7%. Now calculate the hydrogen ion concentration and the percent dissociation of HF in a solution containing 1.0 molar HF, just like before, but also this time we have 1.0 molar NaF, the salt. Okay, so the first part, we did that problem in a prior video. In a prior video, we calculated the percent dissociation of 2.7% for hydrogen ion. Now they want us to do it all over again using an environment where we have 1.0 molar HF and 1.0 molar NaF. Now they give us the Ka for HF, it's 7.2 times 10 to the minus fourth. We find out that the H2O we don't have to worry about, and the Na plus we don't have to worry about. Those guys are neutral. We learned why both of those were neutral in section 14. So I am drawing the dissociation reaction for HF. HF goes to H plus F minus. Now the initial concentrations here are different for the very first time. We have two initial concentrations. Not only do we have the 1.0 HF like we've had in all of times prior, now we have a common ion. 1.0 molar F minus is around to begin with. So we fill in our gaps here like we've done in our ice tables many times before. And we have Ka equals 7.2 times 10 to the minus fourth equals H plus concentration times F minus concentration all over HF concentration, right? This is my equilibrium expression, products over reactants. And that boils down to X times 1.0 plus X all over 1.0 minus X, which we can simplify because Ka is small. 7.2 times 10 to the minus fourth equals X equals H plus. So this time the H plus concentration is 7.2 times 10 to the minus fourth. Okay, that's much smaller than the previous concentration of H plus, which was 2.7 times 10 to the minus second molar. Okay, the addition of that 1.0 molar initial F minus concentration in the top right of my ice box, my ice table box, by the Chatelier's principle, that is going to have an effect. And so we're not going to move to the right after time zero as much as we would have in the past. Okay, so it says here, smaller than previous H plus concentration of 2.7 times 10 to the minus second molar, which means that the additional F minus concentration from NaF shifts equilibrium to the left away from the H plus concentration. All right, that's that. Now let's get to the percent dissociation of HF. We will expect our percent dissociation to also be smaller, right? Well, percent dissociation is my hydrogen ion concentration all over the initial HF concentration times 100%. 7.2 times 10 to the minus fourth all over 1.0 times 100%, 0.072%, much smaller than 2.7. Okay, HF dissociates much less when NaF is present in solution as well because of the common ion effect. All right, so double lines there. First video, we're already getting to buffer solutions, okay? So I'm going to give you some background information on buffer solutions, and then we'll round out this video with our first sample problem on making a buffer. So buffered solutions or buffer solutions, these occur with acid-base reactions containing, you guessed it, containing a common ion. Okay? And that common ion arrives in the form of a salt, where the counter ion is neutral. So buffer solutions occur with acid-base reactions containing a common ion. A buffered solution this is a great definition of a buffer solution. A buffer solution is a solution that resists a change in pH upon the addition of hydrogen ion, acid, right? Or OH minus ion, base. So think of this, a buffer solution is a solution where the pH goes up or down very little, even though I'm adding a really strong acid or a really strong base to the situation. So somehow the really strong acid or really strong base is going to get quenched and replaced by something much weaker that doesn't affect the pH so severely. All right. So top of the next page of notes here, it says the following. Buffer problems are nothing more than the weak acid or weak base solutions that we did a lot of in section 14 with the addition of a common ion, and they are solved using the ice method. Okay, we'll learn later on in section 15 about something called the Henderson-Hasselbalch equation, but for right now, let's just assume that we're going to use the ice method to solve these. And that last problem I did, where the common ion was 1.0 molar of F minus initially, the top right of my initial row in the ice table, that's really the only difference here. Okay, so let's do a last example for this video. It says a buffer solution contains 0.50 molar acetic acid, and they've given us a Ka of 1.8 times 10 to the minus 5, and 0.50 molar sodium acetate. Calculate the pH of this solution. So we've got acetic acid, a weak acid, and we've got a salt, sodium acetate. Acetate is going to be my common ion, right? So my major species, acetic acid and acetate, I'll have arrows underneath both of those. Na plus is neutral, water is neutral. Both of those, the reasons why those are neutral, we talked about in section 14. So I'm going to stretch out my dissociation reaction and get my initial, my change, and my equilibrium. Put a box around that. That's going to become my ice table. And this is my ice method. Now, what are my initial concentrations as I dissociate my weak acid ever so slightly? Remember, weak acids don't dissociate that much, but they do a little bit. Initially, 0.50 molar of the weak acid, also 0.50 molar of the common ion C2H3O2 minus. You apply your minus x's and your plus x's, and you come up with 1.8 times 10 to the minus 5th down there on the bottom, below the box, equals products over reactants equals x times 0.50 plus x, all over 0.50 minus x. This cleans up to be x times 0.5, all divided by 0.5. So, top of the next page of notes, it says 1.8 times 10 to the minus 5th equals x equals H plus concentration. So in the last two examples that we've done, the Ka is equal to x, which is equal to H plus concentration. That isn't always true. It just happens to be true in these two cases. pH equals minus the log of H plus, which is minus the log of 1.8 times 10 to the minus 5th. Therefore, my pH is 4.74. So the pH of a buffer solution of HC2H3O2 and its common ion C2H3O2 minus, the pH of this is 4.74. And we would not expect the pH of this buffer solution to go up very much if I added really strong OH minus to it. And we wouldn't expect the pH to go down very much if we added a really strong acid to the solution. Why is that? How does that work? We'll see that in the next few videos, okay? So the next few videos are coming up, and I want you to remember this problem because I'm going to do a problem just like it in the next video that requires us to remember this, okay? What does it say down here? It says now, because this is a buffer, the pH 4.74 solution is a buffer, it resists a change in pH upon the addition of acid, H+, or base, OH-. How exactly? I'm going to show you that right now in video number 2, which is coming up. Okay, so stick around for that.